Recall that the electric field around a charged object tells us the force that a positive unit charge would experience if we placed it there. Recall also that we draw electric fields using field lines. We now ask the question, what would the electric field be around a combination of charged particles? A simple example would be two positive charges next to each other. At each point in space, we must take the field from each charge individually and combine them, resulting in a new overall field vector at that point in space. For example, at the midpoint here, the field from both charges are the same strength and point in opposite directions, and so they cancel and the field disappears. Up here, the sideways components of the field from each charge cancel each other, but the upwards parts reinforce each other, and so the new overall field points upwards. We combine the two fields in this way over all space, and we look at the pattern. When we draw it with field lines, the resulting electric field for two positive charges next to each other looks something like this. You can see the zero electric field in the center and the upwards pointing field up here. This is what it would look like when we have a positive and negative charge next to each other. This method is how we figure out the electric field around any charged object. We just have to add up all the individual electric fields from all the particles within it. This is clearly very complicated for most objects, but let's take a simple case. A very wide, positively charged plate, which is made up of millions of charged particles. Like in the case of two particles, in areas above the plate, the sideways components of the force fields from each individual particle cancel and the upwards part reinforce, and so you're left with a straight electric field which points upwards above the plate, and at every point above the plate, the strength of this field is the same. If you instead have a negatively charged plate, it would have the same field, but it would be attracting rather than repelling. And when you make a combination of the two like this, what you get is a uniform electric field pointing from the positive plate to the negative plate, with the field lines starting and ending at the charges on the plates. I am now going to introduce the idea of electric potential energy. If we imagine holding a positive unit charge in between the two parallel plates we spoke about before, we know that it will be pushed towards the negative plate. This means that if we wanted to push it to the positive plate, we would need to input some energy. How much energy would we need to input? Well, we'll need to push with a force the same size as the electric field in the opposite direction if we want to be able to move this charge. And the work we have done if we push a charge a distance d is that pushing force times that distance d. So we've expended this energy to push this charge closer to the positive plate and hold it in a new position. But where's that energy gone? It's gone into increasing the electric potential energy of the unit charge. This is similar to the increase in the gravitational potential energy of a heavy bag when we carry it up some stairs. If we were to instead just let the electric field push the unit charge from the positive to the negative plate, it would lose some of its electric potential energy and transfer it into kinetic energy, speeding up. Just like throwing a bag off the top of a building will make the bag lose gravitational potential energy and transfer it to kinetic energy. When we have two parallel plates with a uniform field E between them, the work we would have to do to push a positive unit charge all the way from the negative to the positive plate would be E times the distance between them, d. This means that the charge must have gained that much electric potential energy. We would therefore say that there is a potential difference, or a voltage, of ED between the two plates. The potential difference, or voltage, between two places is therefore defined as the difference between the electric potential energy that a unit charge has as it goes from one place to the other. Notice that we can rearrange this equation and we get the electric field in terms of the voltage and the distance. And this is the way you usually see it. Whenever we talk about energy, we speak about the change in energy between 2 points. And so it's always important to introduce a reference zero energy point that we can say that all other energies are relative to. For example, when we're dealing with gravitational problems, we usually use the Earth's ground level as the reference zero energy point. With our two parallel plates, let's say that we know the potential difference between them is 5 volts. A reasonable reference point would be to call the negative plate 0 volts and the positive plate 5 volts. If we wanted, we could call the negative plate 2 volts and the positive plate 7 volts, as long as the difference between them is 5 volts. What about measuring the electric potential energy of a unit charge around a charged object, rather than between these parallel plates? Where would be a good reference point to call zero energy? We know that the field decreases as we get further away from this charged object, and eventually it will go to zero as we head towards infinity. For this reason, it is convention to choose the universal reference point of electric potential around a charged object to be at an infinite distance away. We then consider the work we must do to move this unit charge from that infinite reference point to whatever point we care about, which is at a distance r from the charged object. Since the electric force will get stronger and stronger, the potential energy will increase faster and faster as we get closer to the charged object, and the graph will look like this. The equation for this curve is that voltage is equal to 1 over 4 pi epsilon naught Q1 over R, which you can just remember as the field strength multiplied by the distance to the object, r. Notice that if the central charge was negative, and so attracted the positive unit charge, the electric potential energy would be turning into kinetic energy as the unit charge got closer, and so its potential energy would be decreasing like this. If we ever want to know the electric potential energy of something that's not a unit positive charge, we again just need to take what the potential energy of a unit charge would be, the voltage, and multiply it by the charge of the object that we care about.
Note that this is both the electric potential energy of the charge Q2 and the charge Q1.